Okay, so I was hoping for some questions. So we have still a few minutes to kill. Anything. Yeah.
You know how you described the work function last time, right?
Uh-huh.
Like the wall, and you basically put in photons, the energy, and the electrons come out with kinetic energy, right?
Uh-huh.
So what if you think about it the other way around? Some, hypothetically speaking, if you could take energy out, would the electrons be done more to the metal nucleus?
If you can put...
If you could, instead of putting energy,
yeah,
you take it out.
take it out.
Hypothetically, like mathematically speaking, you can't do it.
Uh-huh.
Would you expect electrons to be bound closer to the metal nuclei?
So essentially you're asking whether it's possible to somehow suck the energy out of the metal.
I don't know whether it's possible. Hypothetically, if it was possible. I don't think it's possible.
Well, it is possible in the sense if you have two materials and say one has a higher work function than another, right? So say one is like this, and this is the barrier for electrons to come out from metal 1, say. And you have another metal connected somehow with a even higher barrier, then potentially you can have a kind of you can take some of the electrons from here to put here, right? Yeah, so it's in a heterojunction of two materials you can have so-called, there is a barrier, the so-called Schottky barrier, but there is possibility for the transfer of some of the electrons because well, essentially they are more comfortable here than there, right?
So it's essentially like a
Yeah, that's right. That's right. That's what in general chemistry you guys studied, and there is a reduction potential for every metal. Say. Right. So that's one way to think about taking electrons, putting it somewhere, because after all, yeah, metals are different in terms of their work functions. All right, so we kind of stopped last time. I wrote the time-dependent Schrödinger equation, and we'll today consider further what this thing is giving us. All right, so this is our equation in the simplest possible case where we have only one coordinate, spatial coordinate x, and so we have one particle. Our Hamiltonian is an operator that takes the function, produces another function, and it's sum of two operators. One corresponds to kinetic energy, another corresponds to the potential energy. And so the kinetic energy part will be explained in details. Why does it look like this today? And the potential is a relatively straightforward part where you just have potential energy like in classical mechanics, right? Dependence of the potential energy on the space and time. And so if you have a system without time-dependent external fields, then your potential without, say, time-dependent fields, electromagnetic fields, say, then V of xt is simply V of x, right? So it only has a space dependence, the potential part, right? So in that sense, there is nothing really different from classical or physics or classical mechanics when it comes to the potential part. But this thing may seem kind of very different from what we would expect from the classical perspective. So in classical physics, if you asked about the kinetic energy, T classical, of a particle, so then what would be the expression that comes to your mind? Yeah. mv squared. That's it, or half of it? Yes, mv squared. Right. So then it turns out that in so-called Hamilton formalism, that's the one way to represent classical mechanics, which is somewhat equivalent to Newton equations, but it's just more convenient to go to the quantum mechanics. And of course, you didn't study probably Hamilton formalism, but just believe me on that. It's more convenient to work not with the velocities, but rather with momenta. And we all know that the momentum of the particle in the simple case is just mv, right? Then, if we use that, and we can substitute v by p divided by m, right, in this expression. And what do we get? M half p squared divided by m squared, right? So then we can cancel one m, numerator and denominator, and the equivalent classical expression will be like this. So this is classical kinetic energy of the particle, which has momentum p, mass m. And so right now you already can see some similarity with the quantum expression, but we are not quite there yet. Now, in order to go from here to here, turns out what we need is we just need to define what the momentum is in the quantum case. And in classical case, the momentum is just this. But in quantum physics, all the properties they have operators associated with them. Okay, so if you have property like momentum, there will be a momentum operator. If you have energy of the system, then the Hamiltonian operator is an operator associated with that property. And we will talk more in details how do we go from the knowing the operator to calculating or predicting the property that then later can be measured in experiment. But there is this one-to-one mapping between property, any property that is observable in experiment, and operators in quantum mechanics. That's why operators are so important. They are not just mathematical objects, they can be related to physical properties. Okay? Now, to contrast the classical mechanics, classical physics, here the property was essentially a function, right? So we had a function of momentum function, velocity function. They are functions of possible positions or time. So if we study, say, some classical particle like this piece of chalk, if I release it, it will start falling and its momentum will grow, right? So the momentum is a function of time. Now that's classical mechanics. The kinetic energy also a function of other functions, so it's also a function itself. But in quantum mechanics, we need to put in the correspondence to every property an operator. And so to get here, we need to define what do we mean by the momentum as an operator. And it turns out that the definition of what momentum is given like with this simple expression. All right? It's a derivative operator multiplied by imaginary unit, h bar, which was discussed before. It's a Planck constant divided by 2 pi. So essentially it's a constant, right? And this I thing is defined by I squared equals to -1 expression, right? Imaginary unit. Now if we have that, which is, as I clearly understand to use just pure magic, right? Why is this? I'm not explaining right now. And hopefully I'll be able to explain it a little bit later. But as I was telling you before, in physics and science in general, things are not always logical. Well, they are kind of logical in retrospect. But first people suggest something and then they check whether that makes sense, considering all the experimental facts, right? So later I will rationalize why the derivative should be here, why I should be here, and h bar, you can think of it also our signature of well, quantum mechanics, and can be considered just a unit thing because it depends on the units of energy where you present your theory, right? But so far, just believe me, that's the definition of the momentum, right? And if we use this definition of the momentum, then all we can just go from the classical expression p squared divided by 2m to the quantum expression where we use operator, right? And the algebra is pretty simple. We need to square this. It's minus I h bar d over dx square and divide by 2m, right? So the question you may have, what does it mean, square operator? And it's actually very simple. Operator operates on function, gives another function. Square of the operator is just operating twice on the function, getting a different function, say h instead of g. G was the function that we obtain if we operate once on f by O, and if we operate twice, we call this O square, right? So what does it mean d over dx squared then? Well, this is just two differentiations, right? And that corresponds to d squared dx squared, right? So the second derivative. And so this is,
Sorry,
yeah.
When you say that that's the definition of momentum, is that the definition of the operator?
That's right. The operator corresponding to a property that you can measure in an experiment with any quantum particle. You can measure its momentum, do an experiment, and this is an operator corresponding to that property.
Okay.
Okay?
So it's not the expression of momentum, it's the operator that...
Yeah, that's all. It's always in quantum mechanics when we're talking about property, for property to mean anything in quantum mechanical context, you need to define what is the operator. You don't know operator, you don't know what the property is. Okay, you cannot talk about this property meaningfully using the quantum mechanics. If you want to describe some property like energy or even color of the molecule, right? So then anything. Then you need to, if you want to do that quantum mechanically, you need to define an operator. That the operators are absolutely essential. And so the logic here goes like in the classical mechanics we have P as a function of M and V, and in quantum mechanics we have an operator defined like this, and once we put this definition of the operator P into the same expression as in classical mechanics, just substitute function P by operator P, then we get the analog of the quantum analog of what is the operator for the kinetic energy, right? And the way we do it, we just continue in this line. Say we have minus IH squared d squared dx squared, and then 1 over 2m, right? So this is a constant. Derivative doesn't affect the constant, and so then we're still kind of thinking in terms of what the operator is, and all we need to calculate is what is minus IH square is. We know that I square is minus 1. What would be minus I squared? 1. Yeah, still minus 1 actually, if you think about, because minus I is minus 1 multiplied by I, right? And minus I squared is minus 1 I multiplied by minus 1 I. So minus 1 gives you 1, but I times I gives you minus 1, right? So then it's minus 1 still. In order to get plus 1, you need to have I multiplied by minus I. Okay, so we'll practice more this complex arithmetics next lecture, but right now, hopefully this is clear. So that minus I squared is minus 1, and h squared is just a constant, so we have minus h bar squared divided by 2m, second derivative with respect to x squared, right? So this is the final expression that I already written here. It's just now derived starting from the classical version of kinetic energy. Then we substitute momentum by its quantum analog, and then going from here, you kind of see how minus h bar squared, yeah.
Okay, so the second derivative in terms of x, right?
Yeah.
That's that section would be a function that you probably give us, and we would have to take the second derivative to get that form of the equation.
So your question is?
Okay, like you say the operator, you got that expression from doing operator squared,
Right.
which is represented in a function EFG, an operator squared that the function is f of h.
You're referring to these expressions, right? So here, with the operator, sometimes it's convenient to put the function on the right-hand side, or consider that there is some function that these operators are acting on, right? So that's what I've done here, but that's not necessary. You can operate with operators like they're just some mathematical objects, and that's what I did. I just squared the operator.
Yes, so my question is that, is it that we're going to get a function in a question that's asking?
Your question then is a function of operator. Is it a function or is it an operator? Can I frame it like that? Yeah. Well, the answer is no, it's still an operator. If you make a function of operators, it's still an operator. It's just a different one. And to understand that, well, this is kind of an example. If we taken an operator, which is a derivative, and we squared it, then you get it's what does the square mean? We define the square of the operator is just an operator acting twice, and that's how we define it. And in the case of derivative, that would correspond to the taking a second derivative, right? But second derivative of what? You still need a function for this operation to give you a result of the function. But by itself it's an operation, right? It's like, give me a function, I will differentiate it for you twice. That's the object, right? And later, actually you can sum operators, d over dx plus d over dy. That's the example where you sum two operators, and then that actually means, we looked at the previous lecture, that it just means that you need to operate with this, say, O1 on the function, and then this is, say, O2, and the O2 acts on the function. So that's what we mean by operation 1 plus operation 2. It's still an operator, but of course to get the function you need to provide the function to operator. Okay? All right. So if this is all makes sense, what we're gonna do next is in this course we of course will learn how to solve this problem and the solving this problem means that when you set up the Hamiltonian operator, you know how to obtain this object, the wave function, because that's the that's the only unknown in this equation, right? So because the Hamiltonian is already defined, it's defined in this weird quantum way where we have operators, but even without calling them operators, I can write down this equation where I'm considering the second derivative of this quantity plus some function multiplied by this function. This function is known, right? And that thing should be left-hand side, and it should be equal to the right-hand side where I have a known constant multiplied by the derivative of this unknown function with respect to t, right? So the solution for the time-dependent TDSE, time-dependent Schrödinger equation, the solution is this function, psi. Now, instead of going and teaching you how to solve this equation, first I want to kind of explain to you why do we want to find this function. Because solving is more difficult than talking about the solution first. And, well, that's kind of a general philosophy. If you are given a job, first you need to understand what's the motivation for doing that job. Otherwise, you may spend like the rest of your life trying to solve this equation, but maybe that's not the quantity you want, or the quantity that needs to be calculated, right? So you want to have some ending in mind before embarking on the task of solving the difficult differential equation, right? And so that's the, I guess, the main topic of the current lecture is what is this psi function is. So we will kind of, why do we need to calculate it? What kind of information does it contain? Okay, so that's the motivation. And it turns out that this function, if you do the following mathematical operation with it, which is in a short notation is written like this. In a sense, you're taking not the square of the function, but the absolute square, where you take a function and multiply by the conjugate of the function. First, I'll tell you the result. So this is very useful quantity, and then I will tell you how to do conjugation for people who may be not familiar with that operation. Now, this turns out to be a kind of key to the defining where the particle is. So if you have a quantum particle, then this defines the probability density to find the particle in a certain, well, in space, essentially. So we have, say we fix time, t is fixed for simplicity. Say t is 10 seconds after the beginning of the universe, right? And then if we found the function and made a square, absolute square is always positive. So we have this, say, so, and it looks like this. So it turns out to answer the question whether a particle can be found between 1 angstrom and 2 angstroms, all you need is to take this quantity and integrate. So find the area under the curve, right? So probability to find, say, electron between 1 angstrom and so electron is between 2 angstroms, somewhere in the space. You just need to integrate between 1 angstrom, 2 angstroms, d over x of this quantity, right? So this is kind of powerful because with classical particles, you know exactly where they are. With quantum particles, it turns out you can have hundreds of copies of identical particles, non-interacting, so there are hundreds of completely identical copies, and you asking yourself, okay, where is my particle? If I measure measure with a device where the particle is, put in the screen, say they're all floating in some space, and you put in the screen, and then the screen is kind of sensitive to impact of the particle, and then screen right away shows you, okay, the particle is here. Well, it turns out that this experiment, the result of this experiment, can be predicted theoretically. That's why quantum mechanics is so powerful. It can predict the results of the experiment, and in order to predict the result of the experiment, we need this psi square absolute quantity. Okay, so then if we know that from some kind of calculation from the solution of the Schrödinger equation, then all we need to calculate the probability of finding particle is to take this integral. And presumably you can always calculate the integral, maybe not analytically, but numerically you always can do it. All you need is just to essentially calculate, split the area onto the smaller pieces and sum them. Yeah. Right, so generally we will talk about this. Yes, we will consider probability in the range from 0 to 1, right? So it's kind of a normalized probability. The function that we will be working with, they always can be normalized so that the probabilities obtained through this integration will always be between 0 and 1. Okay, and that's just a convenience. Okay. All right, so now let me just clarify what this operation is and why this quantity will always be positive, because probability cannot be negative. That's one thing you probably know just from the kind of general understanding of what probability is. So it is this operation, which is called conjugation. Conjugation is very, very important. So if you don't do that, it turns out if you just take the psi squared, this quantity is not necessarily positive. That's the problem with it. And the conjugation makes this psi absolute value squared always positive. Well, mathematically speaking, mathematicians, they make a distinction between positive and non-negative. So this is actually non-negative because it can be 0, and 0 is not positive, right? So the absolute square always non-negative because the probability cannot be, or probability density cannot be negative. So it's important to have non-negative quantity as a probability density. Now, what is conjugation and why does it make the job done? So let's say if we work with a complex number a plus ib, that's the typical way of writing complex numbers, right? Then, and it turns out the function itself, because there are i's flying around, I here, and there was an I in the definition of what was the momentum operator. So i's were flying around, and then it turns out that in general this function is a complex object. So it has real part and imaginary part. B times I, that's the imaginary part. And this is the real part. Okay, so the conjugation operation, Z star, is a very simple operation. It's probably the simplest operation out there, because you don't need to add, subtract, divide to do any of that. All you need is to substitute whatever sign in front of the I was to the opposite one. So if there was a plus IB, you make it a minus IB. And just to show you an example, say Z is 5 minus 3I, what would be Z star? 5 plus so I3 or 3I, doesn't matter. Right. So that's the conjugation. Now, why does it make everything positive? Like, why, if you multiply Z star with Z, you get always positive number? That can be easily seen by just doing the algebra. 5 minus I3, that's the Z part, multiplied by 5 plus I3, that's the Z star, what do we get? We multiply 5 with 5, 25, right? Then we multiply minus I3 with 5 minus I15, right? 5 times 3 is 15. And then we do the same thing with 5 multiplying I3. That's a plus I15, right? And then we multiply minus I3 with plus I3. And here what do we have? We have minus I3 say plus I3, right? So I times I gives you minus 1, but there is another minus. So together they give you plus, and 3 times 3 is 9. So the whole thing is just 9. And it's real, it's positive. This is real and positive because it's a square of the real part. Now, magically, the real times imaginary and the imaginary times real, they always will have opposite signs, and so they cancel out. Okay? And so you have eventually, as a result, 25 plus 9, right? Which is 34. Okay? It's a positive number, and that's what we wanted. Now, you can imagine if you do, instead of z star, if you do z times z squared, essentially, the result will be different because you get 25 initially, then say you get minus I3 twice times 5, so minus I15, minus I15, and then you will get minus I3 twice essentially squared with say positive sign here and say minus I3, right? And because it's twice minus I, then it gives you still minus 1, and this thing will be minus 9, right? So you get minus 9, which in the cases where you have instead of 5 here, say 1, can overpower this 25. But even if we don't care about positive or negative, the challenge with this is that it actually has a complex components which do not cancel out, right? They always will have the same sign, and this number can be positive, can be negative, and can be real and complex. So it's a recipe for the troubles. Now, in this case, when we do the conjugation, we always can get the non-negative function. So now I illustrated that with numbers. In the lecture notes, actually, I have the same thing written with functions. You can easily repeat the whole consideration of instead of z, you can write down, say, psi equals f of two variables x and t plus I g of x and t. So these functions are real functions, that's the condition, but the psi, because you have ij, it can be complex. Now psi star is f xt minus I g xt, right? And here you go, you can do the multiplication and find that psi squared will be f squared minus plus g squared. And then if you do just psi squared, then you get f squared minus g squared, which can be negative. And this guy cannot be negative. It's always non-negative. Because no matter what f and g as the functions are, they are real functions, and if you square real functions, they always will be squares always will be positive, right? But if you do the square of the function, then first of all you don't have positive, but you have negative minus g squared, and so g squared can overpower f squared for some regions, and also you have the complex part 2fg, right? So that's another unpleasant part of the normal square. Okay, so that's why for the mathematical, for the having the right math for the physics that we eventually want to, or chemistry that we want to extract from the solution of the Schrödinger equation, this quantity is the one that is meaningful. Function itself or its square is completely meaningless. Okay, so in general chemistry, you've probably been introduced to such objects as orbitals, right? So orbitals, what are they? They are essentially the wave functions plotted. Or sometimes people plot some linear combination of orbitals. But in reality, if you, in reality that is meaningless. What is meaningful is the absolute square of the orbital function. Okay, so that is always positive and presents the probability density to find the electron. Okay, now I keep saying probability density, and we want to get confirm that you actually understand what does that mean. Do you understand what the difference between probability and probability density? No. Okay, but you probably feel already at this point that they are somehow related. They have the same word, probability, in them. Right? So let me clarify that difference. Now, with probabilities, probabilities versus probability density, because this is probability density. Probability density. Okay, so the concept of probability in general appears when we talk about random variables. So like they're random. They're random. The simple example would be rolling dice, right? So you have a dice, you roll it, you get a number from 1 to 6. It's just a normal dice. And dice is not loaded or anything. It has kind of the same equal probability of getting from 1 to 1, 2, 3, 4, 5, and 6. That's example number 1, say. And we can discuss what this randomness means. That because potentially, if you know all the forces, and the dice is a classical object, if you know all the forces, how is it thrown, what the initial position and velocity, and where does it fall, so you can actually predict what will be the result. 1, 2, 3, 4, 5, solving the Newton equations for the dice and everything. So you'll probably be banned from casinos, but you can do it, right? So, or on a computer you can calculate what will be actual result. The trouble is that we don't know all the forces at the that's why it's kind of random, right, for us. So it's randomness here represent that our information about the object is limited. So we don't have initial conditions for solving the Newton equations. But if we knew exactly what the force, everything, then we can solve and obtain the deterministic solution for the Newton equations, right? But we're not going to go there. So the randomness here, to illustrate, is just a limited amount of information. We can have these outcomes, and these are discrete variables that we can have. So now, what is the probability of getting one of them, right? So how do we define the probability in general? It's the number of outcomes that give us 2, and number of such outcomes, So I'm talking about probability of getting 2 if you throw a dice. It's number of outcomes that give 2 divided by the total number of outcomes, number of total outcomes. So say the normal dice has only 6 outcomes, right? It cannot be on the vertex, or it cannot be on the corner. It cannot end up there, right? But potentially, if we're not talking about real dice, but some other dice, then the number of outcomes can be more than 6, right? And that would be a different problem. In this problem, though, the number of outcomes that give us the number we're interested in, 2, is just 1. There's only 1, 2 in the whole dice. Other numbers are different, right? And then we divide 1 by the total number of outcomes. There are only 6, right? So 1/6 is the probability to get number 2 when you throw it, the dice, random, right? Now, if you say go into the casino and play on even, like that the outcome will be any even number, what would be the probability of that? 1/2. How did you calculate that? So by the same equation, right? So 2n, that's a general representation of even numbers. So you got 3 here and 6 there, and so this is 1/2, right? So this is a probability in the discrete case. Now, it turns out that when it comes to measuring, say, heights, sizes, not just discrete variables, when it comes to measurement, very frequently we need to go beyond discrete numbers. Say if you go on the field and measure the say size of the or weight of the watermelon, okay, like you have a field full of watermelons, and you can go with your weight measuring device, some kind of scale, and you measure what's the weight of this watermelon, what's the weight of that watermelon, and so on and so forth. So weight can be, well, example 2. So weight of the watermelon, say, can be mass of watermelon, can be in the range between, say, 0, yeah, let's say 0 to 10 kilograms, right? And so anything in between 0 and 10 kilograms could be a weight. And if you now think, okay, what's the probability of getting, let's try to apply the same kind of logic, and we'll see that this logic is somewhat troublesome to deal with the continuous variables. If I say, okay, what's the probability to find watermelon which weighs exactly 5 kilograms? 0, right? So why is it 0? Yeah, that's right. So if you, practically speaking, if you go with a really, really accurate scales and then you start measuring watermelons, even if you find something close to 5, it's always going to be, it could be 5.000001, 2, 3, and so on and so forth. So it's never going to be exactly zeros up to infinity, right? So all these zeros cannot be, like all these decimal points, they cannot be 0. All these figures cannot be exactly 0. You would need infinite precision, and then still with infinite precision there is an infinitely small chance to get all these points to be 0, right? So that means that one particular point has a 0 probability, right? And so how do we really deal with the situations like with the continuous variables? Well, it turns out that convenient way of doing that would be to create a function that is called probability density, right? And in this case of, say, watermelons, so this is a mass, and like it starts somewhere, this is 0, and then end somewhere, right, and say this is 10 kilograms. So, or just to make it more, or like say 100 kilograms. So there's no watermelon higher than 100 kilograms for sure. There is zero probability of finding that. But then it's a continuous function, and if you say, you only can ask questions like, okay, what's the probability to find a watermelon which has a weight between 5 and 6 kilograms, right? And so what do you do for that? You count all the watermelons that are higher than 5 but lower than 6 in this range, 5, 6, and divide by the number of all watermelons, right? So this will be a probability in this range, and that will be some reasonable number between 0 and 1. So how do we obtain this number? For that we need to have a function. Let's call it m, it's mass. Let's call it rho m. So it's a probability density related to the mass, and m can be even an argument, right? So what do we do to get the number of watermelons between 5 and 6 kilograms? Well, it's an integral of this rho of m, dm, integrated over mass from 5 to 6, right? That's this number. It's a number of watermelons between 5 and 6. And then all, how do we obtain number of all watermelons? Well, for that we need just to integrate from 0 to potentially infinity, right? Or to some realistic, in this particular case we can go up to 100. Doesn't need to be up to infinity, but to be safe, if we do math, why not to go to infinity? So we can go to infinity. If we know the function rho of m, we can integrate from 0 to infinity, and that will definitely cover all watermelons, right? So here rho is not a probability. The integral of rho is a probability. But rho itself is just a function, right? And to get the probability, you need to integrate that function in between certain limits, okay? Now, this rho function is the closest so far to this absolute value of psi x t squared, okay? So this is probability density to find particle for a particular time. Okay. Now, if we also look at the question about the 0 and 1, like whether always the probability between 0 and 1, then we kind of get into the situations where, well, in order for, well, like this ratio between number of watermelons between the 5 and 6 kilograms and number of all watermelons, it's always going to be between 0 and 1, right? Because this is always positive number, and it's always lower than the number of all watermelons, right? But if we're talking about the probability density, we can actually do so-called normalization procedure here in order to, instead of operating with rho of m, we can operate with a function. I'll put tilde on it, subscript n, let's say, subscript n. That function is defined so that the integral over the whole range of this normalized probability density will be 1. Okay? And that's convenient because then with this probability density, I can simply obtain this necessary probability by just integrating between 5 and 6 the normalized rho of m. Instead of worrying about taking this integral, I will create now a function that will give me probability to find the watermelon between 5 and 6 kilograms by just operating with one function. How do I do that? So all I need is actually to define this rho of n m as rho of m, the function that I presumably already have, divided by the integral from 0 to infinity rho of m. Let's put the m prime so that this m inside the integral will be not confused with this m, which is an argument of the function. Okay? So because when I take this definite integral, or kind of indefinite, because there is an infinity there, an upper limit, but this is still a number, right? So there is no m dependence of this number. M is integrated. And m here is an argument. And that's how I define my new function that without any division then will always be giving me the probability if I say want to obtain the probability to find the watermelon between A kilograms and B kilograms, then all I need is take this function and integrate between A and B. Okay? So that's simple. So that's the main difference between probability and probability density. So probability density is a function which, if you integrate, it will give you probability. But itself, it's not a probability. Any questions? Yeah.
So we're looking at orbitals as a probability density. How can we connect that to chemical bonds? Like hydrogen has an s orbital.
Right.
And we know that the electron is in that anywhere in that density.
Right. With certain probability, yeah.
And we know it's bonded to carbon, for example. Is that just like a frequency that those electrons densities overlap?
Okay, so when we go from the interesting part, there are multiple interesting questions that are in your question, because say if you have hydrogen, right, and we know it's like a S type of orbital that is, although it does need to be S, if you shine the light, excite hydrogen, it could be P, D, and so on and so forth, right? But say it's S, it's a spherical. First question which always puzzles people when it comes to the electrons is like, or atoms, what's the size of the atom, right? So where do we stop, right? So it's like with the watermelon problem, we can go up to 100 or up to infinity. And so if we go, but the problem is that if we go up to infinity, then the hydrogen atom kind of covers the whole universe, right? But if you solve the Schrödinger equation for hydrogen atom in the kind of ground state, then this density of the hydrogen atom will depend on the distance from the nucleus exponentially, like alpha r, where alpha is a constant, r is the distance. So even at 50 miles from the nucleus of the hydrogen, there is still non-zero value of the density, right? So, and usually now, when it comes to kind of people like to have some clear definition, some clear cuts, and so you can then define, okay, if I integrate this density from 0 to some value, some a, then I would like to have 99.99% of the all electron density in that sphere. So that is my definition of what the size of the hydrogen atom, right? So this number is the size, the radius, but that radius should encompass 99.99. But it's completely arbitrary, right? After all. But there is some arbitrariness there. And now back to your original question, say there is a carbon here, and we have some kind of sigma bond, right? Then if you solve now the Schrödinger equation for carbon, hydrogen, and then carbon, say methane has more hydrogens there. So if you solve that, you will see that the total density, because electrons are actually indistinguishable, so the total density in that system will have some increase in between the bonds, right? And that corresponds to the bonding, that some increase of the total density in between the two atoms, right? So because they kind of, you can think of those two waves constructively interfering. It's like one has a maximum in one area and another has a maximum, and that's why they kind of have a
have their own wave function that can operate on each other in a way that will reduce the material.
Yes, but the language you use right now is not exactly, well, it's not very precise. Functions, first of all, do not operate on each other. Functions, you can sum functions together, and what happens in this problem, like this, you probably heard again in the general chemistry, atomic orbital, linear combination of atomic orbitals that are forming molecular orbitals, right? So you kind of solve Schrödinger equation by making linear combination of atomic orbitals and trying to find the coefficient in these linear combinations to describe what molecular orbital is. And you're going to be getting the molecular orbitals as solutions of Schrödinger equation problem, right? And so that's how you kind of you put these two waves together, and Schrödinger equation tells you what's the proper interference between them. Okay, that then defines the chemistry. Okay, cool. Any more questions? So next time I'll show you some simple examples how this object behaves for simple problems like moving in the free space, moving one single particle on the plane. So yeah, there will be some movies.